Welcome back, fellow dreamers, to the Sleepyhead Geographer. Tonight we are going on another peaceful journey across to our sleeping world. We're going to travel somewhere truly special, not across oceans or continents, not through forests or deserts, but down into the very heart of our planet itself. We're going to visit a place that most of us will never see, yet it shapes every single day of our lives. Feel your body relaxing into your bed, your breathing becoming slow and steady. Tonight, we're going deep into the earth to discover the hidden engine that has been working tirelessly for over 4 billion years. An engine made not of metal and gears, but of rock and heat, pressure and time. Beneath the solid ground where we walk, beneath the familiar world of trees and buildings, roads and rivers, lies something magnificent. A vast, slow-moving ocean of hot rock that we call the Mantle. It's a place where temperatures would melt steel in seconds, where pressure would crush diamonds, where time moves in millions of years rather than minutes. Yet this seemingly impossible place is the true powerhouse of our planet. Think about it for a moment. Every mountain you've ever seen, every valley, every coastline, even the continents themselves, they all exist because of what happens in this hidden realm. The Mantle is Earth's silent architect, constantly reshaping our world from below. The ground beneath your feet right now sits on a raft of rock that floats on this enormous sea of hot stone. We often think of the Earth as solid and unchanging. After all, mountains seem permanent, don't they? The ground feels firm beneath our feet. But our planet is actually more like a living thing, breathing slowly through cycles that span millions of years. And the Mantle is its heartbeat, pumping heat and movement through every layer of our world. We'll journey through the formation of this incredible realm billions of years ago, when our planet was young and violent. We'll explore its structure, layer by layer, like reading the pages of the oldest book ever written. We'll discover what it's made of. Rocks with beautiful names like olivine and pyroxene, minerals that exist nowhere on Earth's surface, yet make up most of our planet's volume. We'll witness the great dance of convection, where hot rock rises like invisible mountains and cold rock sinks like slow waterfalls, creating currents that never stop moving. We'll see how this hidden motion drives the movement of continents, builds mountains, opens oceans, and creates the very ground we stand on. We'll learn about the brave scientists who have spent their lives trying to understand this unreachable place. Using earthquake waves like X-rays, they've mapped a world more mysterious than the deepest ocean trench. We'll discover the ingenious ways they've brought pieces of the Mantle to the surface, and what those samples tell us about the deep history of our planet. And we'll explore what all of this means for our world today, how the Mantle continues to shape our climate, our continents, even our future, how this ancient system connects to everything from the air we breathe to the metals in our phones. The Mantle is not just geology. It's the story of how our planet became the only world we know that can support life. It's the tale of an engine so vast and powerful that it has been running since before the first life appeared on Earth, and will continue running long after the last stars fade from the sky. As we begin this journey together, let your mind drift down through the familiar surface of our world. Past the soil where plants grow their roots, past the bedrock that foundations rest upon. Down, down, through layers of increasing heat and pressure, until we reach the boundary between the world we know and the world we're about to discover. This is where our story begins. In the deep, ancient darkness where Earth keeps its most powerful secrets, where temperatures hot enough to melt copper meet pressures that could compress coal into diamonds, where time itself seems to move differently, where changes that would take seconds on the surface unfold over millions of years. So close your eyes and let your imagination travel with me. We're going to visit the engine room of our planet. We're going to explore the mantle, Earth's hidden heart that beats with liquid stone and breathes with currents of molten rock. We're going to discover how this invisible realm creates the visible world we love. Now travel back in time together, back to the very beginning. Over 4.5 billion years ago, when our solar system was nothing more than a swirling disk of dust and gas around a young, angry sun. Back then, there was no Earth as we know it. No blue skies, no oceans, no solid ground to stand on. Instead, there were countless pieces of rock and metal, ice and dust, all slowly coming together in a cosmic dance of creation. Picture this ancient scene in your mind. Imagine chunks of rock, some no bigger than pebbles, others as large as mountains, all gradually being drawn together by gravity's invisible hand. As these pieces collided and stuck together, they released enormous amounts of energy. Each impact was like a bomb going off, heating the growing planet from within. The early Earth was not the peaceful, cool world we know today. It was a molten ball of liquid rock, glowing like a star against the darkness of space. This was the birth of our planet's mantle. Not formed all at once, but slowly, violently, through countless collisions that lasted for millions of years. Each meteorite that struck the growing Earth added more heat, more pressure, more material. The planet was so hot that there was no distinction between solid and liquid. Everything was molten, everything was in motion, everything was changing. During this violent birth, something remarkable happened. The heavier materials, mainly iron and nickel, began to sink toward the center of this molten world. The lighter materials, rich in silicon and magnesium, remained closer to the surface. This process, called differentiation, was like watching oil and water separate, but happening inside a ball of liquid rock over 1,000 degrees hotter than any volcanic lava we see today. As millions of years passed, the bombardment of meteorites gradually slowed. The young Earth began to cool, slowly and reluctantly. The outermost layer started to form a thin, fragile crust, like skin forming on cooling milk. But beneath this thin shell, the mantle remained hot, restless, and very much alive. The early mantle was nothing like the organized layers we find today. It was a chaotic mixture of molten rock, constantly stirred by the heat radiating from Earth's core and the continued impacts from space. Massive currents of liquid stone rose and fell through the planet's interior like slow-motion thunderstorms made of molten rock. Then came one of the most dramatic events in Earth's history. A Mars-sized object, which scientists call Theia, smashed into our young planet with unimaginable force. This collision was so violent that it blasted enormous amounts of material into space, material that would eventually form our moon. But it also had a profound effect on the mantle. The impact reheated the entire planet, essentially melting it all over again and creating a vast ocean of liquid rock called a magma ocean. This magma ocean was like nothing we can imagine today. It may have been over 1,000 kilometers deep, covering the entire surface of the planet. Within this molten sea, the process of differentiation continued. Heavier minerals sank, lighter ones rose, and slowly, very slowly, the mantle began to take on the layered structure we recognize today. As the magma ocean gradually cooled and solidified, it left behind the first permanent mantle rock. These ancient materials, formed over 4 billion years ago, still exist deep within our planet today. They are like time capsules, preserving the conditions and composition of Earth's earliest days. Some of these primordial rocks occasionally make their way to the surface in volcanic eruptions, giving us precious glimpses into our planet's violent birth. The cooling mantle began to develop its own personality. Convection currents started to organize themselves into more stable patterns. Hot rock rose from deep within the Earth, cooled as it approached the surface, then sank back down to be heated again. This cycle, which continues to this day, began to shape the mantle into distinct layers and regions. The upper mantle, closest to the surface, cooled faster and became more viscous, like thick honey. The lower mantle, still under enormous pressure and closer to the hot core, remained more fluid and mobile. Between these layers, transition zones formed where the crystal structure of minerals changed under the extreme conditions, creating boundaries that still puzzle scientists today. As the Earth continued to cool, water began to condense from the atmosphere and collect on the surface, forming the first oceans. But the mantle's influence was far from over. Even with a solid crust forming above it, the mantle continued to push and pull at the surface, creating the first continents, the first ocean basins, and the first hints of the plate tectonic system that would eventually shape our modern world. During these early billions of years, the mantle was much hotter than it is today. The radioactive elements scattered throughout its volume were more abundant and generated more heat. The convection was more vigorous, the movements more dramatic. The surface of the Earth was constantly being recycled, with new crust forming and old crust being swallowed back into the depths. This was also the time when the mantle began to develop its chemical complexity. Different regions started to take on slightly different compositions as various processes sorted and separated materials. Some areas became enriched in certain elements, while others became depleted. These chemical signatures, like fingerprints of the early Earth, still exist in the mantle today and help scientists understand how our planet evolved. The early mantle was a forge where the raw materials of our planet were processed and refined. It was here that the various rock types that would eventually form continents were first created. It was here that the systems that would regulate Earth's temperature and climate began to develop. And it was here that the stage was set for everything that would follow in Earth's long history. As we imagine this ancient time, we can almost feel the restless energy of the young mantle. The slow, powerful movements of rock heated to temperatures that would vaporize water instantly. The gradual organization of chaos into the layered system that would become the stable foundation for all life on Earth. The birth of the mantle was not a single event, but a process that unfolded over hundreds of millions of years. A process of cooling and heating, mixing and separating, destruction and creation. By the time this formative period was complete, our planet had developed the deep engine that would power its geology for billions of years to come. This is the origin story of the hidden realm beneath our feet. Born in violence and chaos, shaped by time and pressure, cooled by the void of space and heated by radioactive fire. The mantle that emerged from this cosmic crucible was ready to begin its long work of building the world we know today. Now that we understand how the mantle was born, let's explore its architecture. Imagine, if you will, that we could take a knife and slice our planet in half, like cutting an apple. What we would see is not a simple uniform interior, but a complex, layered structure more intricate than any building humans have ever constructed. The mantle is enormous beyond easy comprehension. It makes up about 84% of Earth's total volume and 67% of its mass. To put this in perspective, if Earth were the size of a basketball, the mantle would be everything except a thin skin of paint representing the crust and a marble-sized core in the center. This vast realm extends from about 35 kilometers beneath our feet all the way down to 2,890 kilometers deep, where it meets the molten iron core. Let's begin our journey downward from the surface, layer by layer, like explorers descending through the floors of a vast underground palace. Our first stop is the boundary between the familiar world above and the alien world below. This boundary, called the Mohorovičić discontinuity, or simply the MOHO, marks the transition from the thin, brittle crust to the hot, slowly flowing mantle beneath. Crossing the MOHO is like stepping from a solid wooden floor onto a waterbed filled with hot honey. The change in material properties is dramatic and instant. The crust, made of relatively light rocks like granite and basalt, gives way to much denser mantle rock, dominated by minerals rich in iron and magnesium. The temperature, which might be only a few degrees above freezing at the surface, suddenly jumps to around 500 degrees Celsius. As we continue our descent into the upper mantle, the temperature steadily rises, reaching about 900 degrees Celsius by the time we've traveled 100 kilometers down. This is hot enough to melt copper, yet the rock around us remains solid. This seems like a contradiction until we remember that pressure increases as dramatically as temperature in this deep realm. The weight of all the rock above presses down with such force that it keeps even this superheated material in a solid state. But this is a strange kind of solid, unlike anything we experience on the surface. The mantle rock is solid in the same way that silly putty is solid. Hit it with a hammer and it will shatter like glass. But leave it alone for long periods and it will flow like thick liquid. This property, called plastic deformation, allows solid rock to move and flow over geological timescales, creating the slow, powerful currents that drive plate tectonics. The upper mantle extends down to about 410 kilometers below the surface. Throughout this region, the dominant rock type is peridotite, a dense dark green rock composed mainly of the mineral olivine. If you could hold a piece of upper mantle rock in your hands, it would feel surprisingly heavy, about 3 times denser than granite. Its dark green color comes from the iron-rich olivine crystals that make up most of its volume. At 410 kilometers depth, we encounter our first major boundary within the mantle itself. Here, the intense pressure causes the crystal structure of olivine to suddenly change, transforming into a denser arrangement of atoms. This transformation creates a sharp boundary called the 410-kilometer discontinuity. Seismic waves speed up as they cross this boundary, revealing its presence to the earthquake scientists who map Earth's interior. Continuing downward, we enter the transition zone, a region that extends from 410 to 660 kilometers deep. This zone is like a pressure cooker, where minerals are constantly transforming into denser forms as the weight above them increases. The olivine that dominated the upper mantle gradually changes into different crystal structures with exotic names like wadsleyite and ringwoodite. These minerals exist nowhere else on Earth except in this high-pressure realm. The transition zone is also thought to be a reservoir for water, not as liquid oceans, but as water molecules trapped within the crystal structures of these high-pressure minerals. The amount of water stored here might exceed the volume of all the oceans on Earth's surface. This hidden water plays a crucial role in the mantle's behavior, making the rock slightly softer and more able to flow. At 660 kilometers depth, we encounter an even more dramatic boundary. Here, the minerals of the transition zone undergo a complete reorganization, transforming into the dense, tightly packed structures that will dominate the deep Earth. This 660-kilometer discontinuity marks the entrance to the lower mantle, a realm so different from the surface world that it might as well be another planet. The lower mantle is a place of extreme conditions that challenge our understanding of matter itself. The pressure here is over 200,000 times greater than atmospheric pressure at sea level. The temperature rises from about 1,600 degrees Celsius at the top to nearly 4,000 degrees Celsius at the bottom, approaching the temperature of the sun's surface. Yet despite these extreme conditions, this region remains solid, held in place by the immense pressure. The dominant mineral in the lower mantle is bridgmanite, formerly known as silicate perovskite. This mineral, which makes up about 38% of Earth's total volume, exists nowhere else in the solar system except under the extreme conditions of planetary interiors. Bridgmanite has a crystal structure so efficient at packing atoms together that it can withstand the incredible pressures of the deep Earth while maintaining its solid form. Mixed with the bridgmanite is another high-pressure mineral called ferropericlase, which contains much of the iron that gives the deep mantle its density. These two minerals, bridgmanite and ferropericlase, form the foundation of the lower mantle, creating a mixture that is both incredibly strong and surprisingly mobile over geological time. The lower mantle is not perfectly uniform. Scattered throughout this vast region are areas where the composition or temperature differs slightly from the surrounding rock. These variations, called heterogeneities, are like rivers and pools in the deep Earth, guiding the flow of convection currents and influencing how heat moves from the core to the surface. Near the very bottom of the mantle, in a thin layer called the D double prime region, conditions become even more extreme. Here, temperatures approach those of the outer core, and the mantle rock begins to show unusual properties. Some scientists believe that this region contains ancient material from Earth's formation, preserved for billions of years in this deep, stable environment. The D layer is also where large-scale structures called large low-shear velocity provinces, or LLLSV pairs, exist. These continent-sized blobs of anomalous material may be the remains of ancient impacts or differentiation processes from Earth's early history. They influence the pattern of mantle convection and may be the source of some of the most dramatic volcanic eruptions on Earth's surface. Throughout all these layers, from the shallow upper mantle to the deep D region, temperature and pressure create a complex three-dimensional structure. The mantle is not a simple layer cake, but rather a dynamic system where different regions interact, exchange material, and influence each other across vast distances and enormous time scales. Understanding this architecture helps us appreciate the mantle's role as Earth's great engine. Each layer has its own properties, its own behavior, and its own influence on the planet's evolution. The upper mantle directly drives plate tectonics. The transition zone acts as a filter and reservoir. The lower mantle provides the deep engine of convection. And the D layer serves as the interface between the mantle's rocky realm and the core's metallic domain. This layered structure, built over billions of years by the interplay of temperature, pressure, and chemistry, creates the framework within which all of Earth's geological processes operate. It is the architecture that supports our continents, powers our volcanoes, and ultimately makes our planet the dynamic, living world it is today. Having explored the mantle's structure, let's now delve into its composition, the actual materials that make up this vast, hidden realm. Imagine if we could gather samples from every layer of the mantle and examine them in a cosmic laboratory. What we would discover is a collection of minerals and elements more exotic than the rarest gems, yet making up most of our planet's interior. The story of the mantle's composition begins with the elements themselves. Unlike the surface of Earth, where we find over 90 naturally occurring elements in countless combinations, the mantle is surprisingly simple in its basic ingredients. The mantle is made up of 44.8% oxygen, 21.5% silicon, and 22.8% magnesium, with iron, aluminum, calcium, sodium, and other elements making up the remainder. These elements don't exist alone, of course. They combine to form minerals, and the mantle's minerals are among the most fascinating materials in our solar system. At the surface of our planet, we're familiar with quartz, feldspar, and calcite. But in the mantle, the extreme conditions of temperature and pressure create entirely different mineral families with properties that would seem magical if we encountered them in everyday life. Let's begin our mineral tour in the upper mantle, where the dominant mineral is olivine. If you've ever seen the green sand beaches of Hawaii, you've actually seen olivine grains weathered from volcanic rock. In the mantle, olivine exists as large, perfect crystals with a beautiful green color that comes from iron atoms nestled within its crystal structure. The upper mantle is dominantly peridotite, composed primarily of variable proportions of the minerals olivine, clinopyroxene, orthopyroxene, and an aluminous phase. Olivine is remarkable because it represents the perfect balance between Earth's most abundant elements. Its chemical formula, MgFe2SiO4, shows how magnesium and iron atoms share space in a framework built around silicon and oxygen. This sharing creates a mineral that is both strong enough to withstand enormous pressures and flexible enough to flow over geological time. The olivine in your mantle right now has been slowly circulating through the planet's interior for millions, perhaps billions of years. Alongside olivine in the upper mantle, we find the pyroxene family of minerals. Clinopyroxene and orthopyroxene are like olivine's cousins, sharing similar chemistry but with different crystal structures. These minerals often contain calcium, giving them slightly different properties and colors. In thin slices under a microscope, pyroxenes display beautiful interference colors that shift from green to purple as the sample is rotated. The third major component of upper mantle rock is garnet, though not the red gems we might recognize from jewelry. Mantle garnets are typically green or orange, and they play a crucial role in the mantle's behavior. Garnet is denser than olivine or pyroxene, so when mantle rock melts partially to create volcanic magma, garnet tends to stay behind in the solid residue. This process helps explain why surface volcanic rocks have different compositions than their mantle sources. As we travel deeper into the mantle, approaching the transition zone, these familiar minerals begin to transform under increasing pressure. The transformation isn't gradual but sudden, like water turning to ice. At exactly 410 kilometers depth, olivine suddenly reorganizes its atomic structure to become a denser mineral called wadsleyite. The atoms are the same, but their arrangement changes to pack more efficiently under the extreme pressure. Wadsleyite has a fascinating property. It can contain much more water in its crystal structure than olivine can. Not liquid water, of course, but hydrogen and oxygen atoms incorporated directly into the mineral framework. This capability makes the transition zone potentially the largest reservoir of water on our planet, containing possibly more water than all the oceans combined. This water isn't available for drinking, but it profoundly affects how the mantle behaves, making it slightly softer and more able to convect. Deeper still, at about 520 kilometers, wadsleyite itself transforms into an even denser form called ringwoodite. Named after Australian mineralogist Ted Ringwood, this mineral represents the ultimate high-pressure form of olivine chemistry. Ringwoodite can hold even more water than wadsleyite, making the deep transition zone an even more significant water reservoir. At the bottom of the transition zone, at 660 kilometers depth, the most dramatic mineral transformation occurs. Here, ringwoodite breaks down completely, separating into two different minerals with entirely different crystal structures. The magnesium and silicon form bridgmanite, while the iron forms ferropericlase. This transformation marks the entrance to the lower mantle's exotic mineral realm. Bridgmanite is perhaps the most important mineral you've never heard of. It makes up about 38% of Earth's entire volume, making it by far the most abundant mineral on our planet. Yet bridgmanite can only exist under the extreme pressures of the lower mantle. Bring it to the surface, and it would instantly transform into other minerals, making it impossible to study directly. The crystal structure of bridgmanite is remarkably efficient at packing atoms together. Silicon and oxygen form octahedral arrangements, with magnesium, iron, and aluminum filling the spaces between. This structure is so stable under pressure that it maintains its integrity even at the base of the mantle, where temperatures approach 4,000 degrees Celsius. Alongside bridgmanite in the lower mantle, we find ferropericlase, a simple combination of magnesium oxide and iron oxide. While structurally simple, ferropericlase plays a crucial role in the mantle's behavior. The iron in ferropericlase can exist in different oxidation states, and changes between these states affect how efficiently the mineral conducts heat and electricity. Recent research has revealed that the lower mantle's composition isn't perfectly uniform. Different regions contain varying amounts of iron, aluminum, and other elements, creating a subtle but important chemical diversity. These compositional variations, inherited from Earth's formation and modified by billions of years of convection, influence how different parts of the mantle behave. Some regions of the lower mantle appear to be enriched in iron, making them denser and affecting their buoyancy. Others contain more aluminum, which changes their thermal properties. These chemical variations help explain why mantle convection isn't perfectly regular, but instead shows the complex patterns we observe through seismic studies. At the very base of the mantle, in the D layer, the composition becomes even more exotic. Here, the extreme temperatures and pressures, combined with interaction with the iron core, create unique mineral assemblages. Some bridgmanite may transform into a post-bridgmanite phase with even higher density. Iron-rich phases that are stable only under these extreme conditions may form. The D layer also appears to contain regions with compositions quite different from the rest of the mantle. These may be remnants of Earth's early differentiation, ancient subducted oceanic crust, or even material from the core that has somehow mixed with the mantle. The exact nature of these anomalous regions remains one of geology's greatest mysteries. Throughout the mantle, trace elements tell stories of Earth's history. Elements like helium, preserved since the planet's formation, provide clues about early differentiation processes. Radioactive elements like uranium, thorium, and potassium generate heat that drives convection. Noble gases trapped in mantle minerals record atmospheric conditions from billions of years ago. The mantle also contains surprises that challenge our understanding of Earth's chemistry. Deep diamonds, formed in the transition zone or lower mantle, sometimes contain intrusions of ringwoodite or other high-pressure minerals. These diamonds serve as time capsules, preserving samples of the deep Earth and bringing them to the surface where we can study them. Even water, which we think of as a surface phenomenon, exists throughout the mantle in various forms. In addition to the water stored in transition zone minerals, water may be dissolved in mantle melts, incorporated into various mineral structures, or even exist as separate hydrogen and oxygen atoms under extreme conditions. The composition of Earth's mantle represents a 4 billion-year experiment in high-pressure, high-temperature chemistry. It's a laboratory where common elements combine in extraordinary ways to create materials with properties we're only beginning to understand. Each mineral, each element, each chemical variation tells part of the story of our planet's formation and evolution. Understanding the mantle's composition helps us appreciate its role in shaping our world. These minerals and elements don't just exist passively in the deep Earth. They actively participate in the processes that move continents, build mountains, and regulate our planet's climate. The composition of the mantle is literally the foundation upon which all of Earth's surface features rest. Now that we understand what the mantle is made of, let's witness its most remarkable property: its ability to move. Despite being solid rock, the mantle flows like an incredibly slow river, creating currents that have been circulating for billions of years. This movement, called convection, is perhaps the most important process happening inside our planet, driving everything from earthquakes to the formation of new continents. To understand mantle convection, imagine a pot of honey warming on a stove. As the honey at the bottom heats up, it becomes less dense and begins to rise. When it reaches the surface, it cools, becomes denser, and sinks back down. This creates a circulation pattern that distributes heat throughout the honey. The mantle works in much the same way, but on a scale so vast and slow that the currents take millions of years to complete a single circulation. The engine that drives mantle convection is heat. At the bottom of the mantle, temperatures reach nearly 4,000 degrees Celsius, approaching the heat of the sun's surface. This heat comes from two main sources: the leftover energy from Earth's violent formation billions of years ago, and the ongoing decay of radioactive elements scattered throughout the mantle. Uranium, thorium, and potassium atoms split apart over geological time, releasing energy that has kept our planet's interior hot for over 4 billion years. When mantle rock near the core mantle boundary absorbs this heat, it expands slightly, becoming less dense than the cooler rock above it. Buoyancy takes over, and the hot rock begins to rise, just like a helium balloon floating upward through the atmosphere. But this is no quick ascent. The journey from the deep mantle to near the surface takes tens of millions of years, making it one of the slowest movements on Earth. As this hot rock rises, it gradually cools, losing heat to the surrounding material. By the time it reaches the upper regions of the mantle, it has become cool and dense enough to begin sinking back down. This creates the return flow of the convection current, carrying cooler material back toward the core mantle boundary. These convection currents organize themselves into enormous cells, like invisible tornadoes of slowly moving rock. Some cells may be thousands of kilometers across and extend from near the surface all the way to the core mantle boundary. Others are smaller and more localized. The exact pattern of these convection cells changes over geological time, but the overall circulation has been continuous since early in Earth's history. The rising portions of these convection currents create what geologists call mantle plumes. These are columns of hot rock that ascend through the mantle like underwater tornadoes made of stone. When a mantle plume approaches the surface, it can create dramatic volcanic activity. The Hawaiian Islands are built on top of a mantle plume that has been active for tens of millions of years. As the Pacific Plate moves over this stationary plume, it creates the chain of volcanoes we see today. Iceland sits on top of another famous mantle plume, which is why this small island has so much volcanic and geothermal activity. The plume brings hot rock close to the surface, creating the conditions for the dramatic geysers, hot springs, and volcanic eruptions that characterize Iceland's landscape. The Mid-Atlantic Ridge, which runs right through Iceland, is fed by this deep mantle upwelling. But not all of the mantle's convection is organized into neat plumes. Much of the circulation happens in broad, sheet-like flows that spread across enormous areas. These flows are harder to detect, but may be even more important for the overall heat budget of the planet. They help distribute the mantle's heat more evenly, preventing any single region from becoming too hot or too cold. The speed of mantle convection is almost impossibly slow by human standards. The fastest moving currents travel at about 10 centimeters per year, roughly the speed at which your fingernails grow. Most mantle flow is even slower, perhaps only a few centimeters per year. To put this in perspective, it would take the mantle rock beneath your feet about 100 million years to circulate once through the entire convection system. This glacial pace might make mantle convection seem unimportant, but its effects accumulate over geological time. The slow circulation of the mantle has mixed and remixed Earth's interior countless times over the planet's 4.5 billion-year history. Material that formed near the surface billions of years ago has been carried deep into the mantle, while deep material has been brought to the surface and incorporated into new rocks. The convection pattern isn't uniform throughout the mantle. The upper and lower mantle may circulate somewhat independently, separated by the chemical and physical barriers of the transition zone. Some scientists believe that subducted oceanic plates, cold slabs of surface rock pushed down into the mantle at places like the Peru-Chile Trench, may pile up at the 660-kilometer boundary, creating a barrier to mixing between the upper and lower mantle. Other researchers argue for whole mantle convection, where currents extend from the surface all the way to the core mantle boundary. Evidence for this includes the discovery of lower mantle material in some surface volcanic rocks, suggesting that deep material can indeed make its way to the surface. The debate continues, but both models agree that the mantle is a dynamic, actively convecting system. Temperature variations drive convection, but they're not the only factor. The mantle's composition also plays a crucial role. Regions with different chemical makeup behave differently under the same temperature and pressure conditions. Iron-rich areas are denser and tend to sink, while magnesium-rich regions are more buoyant and tend to rise. These compositional variations create complex flow patterns that wouldn't exist in a chemically uniform mantle. Water content also influences mantle convection in surprising ways. Even though the mantle contains only tiny amounts of water by weight, this water has a profound effect on how the rock behaves. Water dissolved in mantle minerals or trapped in their crystal structures acts like a lubricant, making the rock flow more easily. Regions with higher water content can convect more vigorously than dry areas, creating local variations in the global convection pattern. The phase transitions that occur at 410 and 660 kilometers depth also affect convection. When rising hot rock reaches these boundaries, the sudden change in mineral structure can either help or hinder the flow. At 410 kilometers, the olivine to wadsleyite transition releases latent heat, giving the rising rock an extra boost of buoyancy. At 660 kilometers, the transformation to lower mantle minerals absorbs heat, potentially slowing or deflecting the upward flow. Mantle convection isn't steady or regular. Like weather patterns in the atmosphere, the deep circulation can change over time. Computer models suggest that the mantle may go through periods of vigorous convection alternating with quieter times. During active periods, more heat is transported to the surface, potentially affecting global climate and the intensity of volcanic activity. The interaction between ascending and descending currents creates complex three-dimensional patterns. Hot plumes rising from the deep mantle encounter cold downwellings of subducted oceanic crust descending from the surface. These meetings can deflect plumes horizontally, creating mushroom-shaped heads that spread out beneath the lithosphere. The thermal and chemical interaction between hot and cold currents generates turbulence and mixing that helps homogenize the mantle's composition over geological time. Recent research has revealed that mantle convection may be organized into distinct superplumes, massive upwellings that dwarf individual plumes like the one beneath Hawaii. Two of these superplumes have been identified, one beneath Africa and another beneath the Pacific. These structures, thousands of kilometers across and extending from the core mantle boundary nearly to the surface, may control the overall pattern of mantle flow and surface volcanism. The African superplume appears to be responsible for the East African Rift system, where the continent is slowly splitting apart. The Pacific superplume may feed the numerous volcanic islands scattered across the Pacific Ocean, from Hawaii to Tahiti. These superplumes represent convection on the largest possible scale, organizing the mantle's circulation into continent-sized cells. Mantle convection also creates more subtle effects that influence the surface world. The rising and falling of convection currents causes the overlying surface to rise and fall as well, creating what geologists call dynamic topography. Regions above upwelling currents are elevated, while areas above downwelling currents subside. This process can create highlands and basins that persist for millions of years, influencing drainage patterns, climate, and the evolution of life. The convection currents also generate variations in Earth's gravitational field. Regions where dense, cold material is sinking create slightly stronger gravity, while areas above hot, buoyant upwellings have slightly weaker gravity. These variations are tiny, less than 1 part in 100,000, but they can be measured by sensitive satellites and used to map the mantle's convection pattern from space. Understanding mantle convection helps us appreciate the dynamic nature of our seemingly solid planet. The ground beneath our feet is actually floating on top of this vast, slowly circulating system. The currents that flow in the mantle have been shaping Earth's surface for billions of years, and they will continue to do so for billions more. Every mountain range, every ocean basin, every continent owes its existence to the endless dance of convection in the mantle below. This circulation system is what makes Earth unique among the planets in our solar system. Mars is too small to maintain vigorous mantle convection, so its surface has remained largely unchanged for billions of years. Venus may have active mantle convection, but its thick atmosphere prevents us from seeing the surface effects clearly. Only Earth has the right combination of size, composition, and thermal structure to maintain the kind of active mantle convection that continuously renews and reshapes the surface. The convection currents in Earth's mantle represent one of nature's most impressive engines. Powered by radioactive decay and primordial heat, lubricated by trace amounts of water, and organized by the complex interplay of temperature, pressure, and chemistry, this system has been running continuously for over 4 billion years. It's an engine with no moving parts except the rock itself, yet it has built continents, opened and closed oceans, and created the dynamic surface environment that makes life possible. As we contemplate this vast, slow circulation of solid rock, we can almost sense the patient power of geological time. The currents flowing beneath us now began their journey millions of years before the first humans appeared on Earth. The heat they carry originated in radioactive atoms that have been decaying since the solar system formed. In the endless dance of mantle convection, we glimpse the deep rhythms that govern our planet's behavior across the vastness of geological time. The slow, powerful circulation of the mantle doesn't remain hidden in the deep Earth. Its effects reach all the way to the surface, creating one of the most important processes in Earth's history. Plate tectonics. The movement of continents, the formation of ocean basins, the building of mountain ranges, and even the distribution of earthquakes and volcanoes. All of these surface phenomena are direct expressions of the mantle's convective flow. To understand this connection, imagine the Earth's surface as a collection of enormous rafts floating on the slowly moving mantle below. These rafts, which geologists call tectonic plates, are pieces of the lithosphere, the rigid outer shell that includes both the crust and the uppermost part of the mantle. There are about a dozen major plates and many smaller ones, each moving independently in response to the currents flowing beneath them. The lithosphere itself is fascinating. Unlike the hot, flowing mantle below, the lithosphere is relatively cool and brittle. It behaves more like a solid sheet of metal floating on honey than like part of the flowing mantle system. This difference in behavior creates a sharp boundary called the lithosphere-asthenosphere boundary, where the rigid plates above meet the flowing mantle below. The asthenosphere, which extends from this boundary down to about 300 kilometers depth, is the part of the mantle most directly involved in driving plate tectonics. Here, temperatures are high enough and pressures low enough that the mantle rock can flow relatively easily. The asthenosphere acts like a lubricating layer, allowing the rigid plates above to slide and move in response to the deeper convection currents. Where mantle convection currents rise toward the surface, they create divergent plate boundaries, places where tectonic plates move apart from each other. The Mid-Atlantic Ridge is perhaps the most famous example. Here, hot mantle material rises up from depth, partially melts as it approaches the surface, and creates new oceanic crust. This process, called seafloor spreading, has been opening the Atlantic Ocean for over 200 million years. As you relax and imagine this process, picture the Mid-Atlantic Ridge as a vast underwater mountain range running down the center of the Atlantic Ocean. Along its crest, new volcanic rock is constantly being created as mantle material melts and erupts onto the seafloor. This new crust pushes the existing seafloor away from the ridge, like a slow-motion conveyor belt carrying the ocean floor away from its point of creation. The connection between mantle upwelling and seafloor spreading isn't just theoretical. Scientists have mapped the temperature and flow patterns beneath mid-ocean ridges and found clear evidence of hot mantle currents rising from great depths. These upwelling currents bring heat and material to the surface, fueling the volcanic activity that creates new oceanic crust. But what goes up must come down, and this is where convergent plate boundaries come into play. Where mantle currents descend back into the deep earth, they create zones where tectonic plates are pulled downward and destroyed. The most dramatic examples are subduction zones, where oceanic plates dive beneath continental plates or other oceanic plates, carrying surface material back into the mantle. The Peru-Chile Trench along South America's western coast is a classic example of a subduction zone. Here, the Nazca Plate, carrying Pacific Ocean seafloor, is being pulled down into the mantle beneath the South American continent. As this cold, dense oceanic plate descends, it creates a deep trench on the seafloor and generates the earthquakes and volcanic activity that characterize the Andes Mountains. The subduction process reveals the intimate connection between mantle convection and surface tectonics. The sinking oceanic plate doesn't just disappear, it becomes part of the mantle's convection system. As it descends, it heats up and eventually loses its distinct identity, becoming part of the general circulation. Some subducted material may sink all the way to the core mantle boundary before being recycled back upward in future convection currents. This recycling process has profound implications for understanding Earth's chemical evolution. Elements that were once part of the atmosphere or oceans can be carried into the deep mantle through subduction, then returned to the surface millions of years later through volcanic activity. Water, carbon dioxide, and other volatile compounds follow these deep cycles, connecting the surface and interior in ways that influence both geology and climate. The mantle's influence on plate tectonics isn't limited to creating new crust and destroying old crust. Mantle plumes, those vertical columns of hot rock rising from great depths, can also drive tectonic processes. When a large mantle plume approaches the surface beneath a continent, it can create massive volcanic provinces that cover millions of square kilometers. The Deccan Traps in India represent one such event. About 66 million years ago, a massive mantle plume created volcanic eruptions that covered much of western India with basaltic lava. These eruptions were so large and long-lasting that they may have contributed to the mass extinction that ended the age of dinosaurs. The plume responsible for the Deccan Traps can still be traced today. It now lies beneath Reunion Island in the Indian Ocean, having been left behind as the Indian Plate moved northward. Mantle plumes can also break apart continents. The East African Rift System, where the African continent is slowly splitting into two pieces, appears to be driven by a large mantle plume beneath eastern Africa. The rising hot rock creates uplift and volcanism, weakening the continental crust and eventually leading to the formation of new ocean basins. The speed of plate motion is directly related to the vigor of mantle convection. Plates move at rates ranging from about 2 to 10 centimeters per year, roughly the speed of fingernail growth. These rates correspond closely to the velocities of mantle convection currents measured by seismic studies. When mantle convection is more vigorous, plates move faster. When convection slows down, plate motion decreases as well. The pattern of plate boundaries around the world also reflects the organization of mantle convection. The ring of fire around the Pacific Ocean, with its numerous volcanoes and frequent earthquakes, corresponds to regions where cold oceanic plates are sinking into the mantle. The mid-ocean ridge system, which forms the longest mountain chain on Earth, marks places where hot mantle material is rising to the surface. Transform boundaries, where plates slide past each other horizontally, also reflect mantle dynamics. The San Andreas Fault in California is a transform boundary where the Pacific and North American plates slide past each other. This motion is ultimately driven by the different convection patterns beneath each plate, creating shear along their boundary. The mantle's influence extends beyond just moving the plates. The thermal structure of mantle convection also affects the elevation of continents and ocean basins. Regions above hot mantle upwellings tend to be elevated, while areas above cold downwellings are depressed. This creates what geologists call dynamic topography, landscape features created directly by mantle flow rather than by surface processes. The Colorado Plateau in the southwestern United States sits about 2 kilometers above sea level, partly because it lies above relatively hot mantle. The high elevation isn't just due to surface uplift, it's also supported by the buoyant mantle below. Similarly, some ocean basins are deeper than average because they lie above regions where cold, dense material is sinking into the mantle. Mantle convection also influences the long-term evolution of continents. The heat flow from mantle upwellings can cause continental crust to become soft and extensible, leading to the formation of rift valleys and eventually new ocean basins. The cooling effect of mantle downwellings can make continental margins subside, creating the broad continental shelves where much of the world's ocean life thrives. The relationship between mantle convection and plate tectonics represents one of Earth's most fundamental feedback systems. Surface processes affect the mantle by controlling where cold material enters the system through subduction. Mantle processes affect the surface by determining where heat and material emerge through volcanism and seafloor spreading. This continuous interaction has shaped our planet's evolution for billions of years. Understanding this connection helps us appreciate why Earth is such a dynamic planet. The mantle's convective engine doesn't just operate in isolation deep beneath the surface. It reaches upward through the entire solid Earth, driving the movement of continents, controlling the distribution of mountain ranges and ocean basins, and influencing everything from earthquake hazards to the locations of mineral deposits. The tectonic plates that carry our continents and ocean basins are ultimately passengers on the mantle's slow but powerful convection currents. Every earthquake reminds us that the ground beneath our feet is part of a vast, moving system. Every volcanic eruption brings mantle material to the surface, providing a direct sample of the deep Earth. Every mountain range represents millions of years of plate motion driven by currents flowing thousands of kilometers below. As we settle into sleep, we can imagine ourselves as passengers on this grand journey. The continent we rest upon is slowly moving, carried by currents of hot rock flowing through the deep Earth. The journey is so gradual that we can't feel it, but it's real and continuous. In the time it takes for us to live our lives, our continent might move a few meters. Over geological time, it will travel thousands of kilometers, crossing climate zones and ocean basins in response to the endless circulation of the mantle below. The mantle lies forever beyond our direct reach, hidden beneath thousands of kilometers of solid rock. Yet through human ingenuity and scientific determination, we have found remarkable ways to study this invisible realm. Like detectives gathering clues from a distant crime scene, scientists have developed techniques that allow us to map, analyze, and understand the deep Earth with surprising precision. The story of mantle exploration begins with earthquakes. Every time the Earth shakes, it sends waves of energy racing through the planet's interior. These seismic waves behave like X-rays in a medical scan, revealing the internal structure of our planet as they travel from their source to recording stations around the world. The first scientists to recognize this opportunity were studying earthquakes not to understand the mantle, but simply to locate and measure the earthquakes themselves. In 1909, Croatian seismologist Andrija Mohorovičić was studying earthquake records when he noticed something puzzling. Seismic waves seemed to speed up suddenly at a depth of about 35 kilometers beneath the continents. This acceleration could only mean that the waves had entered a different type of rock, denser and more rigid than the crustal rocks above. Mohorovičić had discovered the boundary between Earth's crust and mantle, a discontinuity that still bears his name today. As seismologists placed more sensitive instruments around the world, they began to map the mantle's structure in unprecedented detail. They discovered that seismic waves travel at different speeds through different materials, allowing them to identify layers, boundaries, and variations within the Earth's interior. P waves, primary waves, compress and expand rock as they travel, while S waves, secondary waves, shake rock from side to side. The behavior of these different wave types provides different types of information about the materials they encounter. The most dramatic discovery came when seismologists realized that S waves, which can only travel through solid materials, were blocked by Earth's outer core. This revealed that the core is liquid, an ocean of molten iron and nickel surrounding a solid inner core. But the mantle, which transmits both P waves and S waves, is entirely solid, albeit hot and slowly flowing. Modern seismology uses networks of thousands of sensitive instruments to create detailed three-dimensional images of the mantle. These seismic tomography studies work like medical CT scans, combining information from many different earthquake sources and recording stations to build up a complete picture of the mantle's internal structure. The results reveal a complex, heterogeneous interior with hot zones, cold zones, and structures that extend from the surface to the core mantle boundary. But seismic waves provide only indirect information about the mantle's composition and properties. To truly understand what the mantle is made of, scientists need actual samples. This presents an obvious problem. How do you obtain samples from a place that's thousands of kilometers deep and hot enough to melt steel? The answer comes from the mantle itself. Sometimes, through volcanic eruptions or tectonic processes, pieces of mantle rock make their way to Earth's surface, where we can collect and study them. These samples, called mantle xenoliths, meaning foreign rocks, are like messages from the deep Earth, carried upward by volcanic eruptions or exposed by erosion of ancient mountain roots. Kimberlite pipes, the volcanic conduits that bring diamonds to the surface, are particularly valuable sources of mantle xenoliths. These explosive eruptions originate deep in the mantle and carry fragments of mantle rock upward so quickly that they don't have time to melt during their journey to the surface. Diamond mines in South Africa, Canada, and elsewhere have yielded thousands of mantle samples that provide direct information about conditions 150 to 200 kilometers below the surface. The xenoliths reveal that the upper mantle is composed primarily of peridotite, a dark green rock made mostly of olivine, with smaller amounts of pyroxene and garnet. Chemical analysis of these samples tells us about the mantle's composition, while the minerals themselves record the temperature and pressure conditions they experienced in the deep earth. Some xenoliths contain tiny inclusions of water, carbon dioxide, or other fluids, providing information about the volatile content of the mantle. Even more exotic are the inclusions found within diamonds themselves. Some diamonds contain tiny crystals of ringwoodite, the high-pressure form of olivine that exists only in the mantle's transition zone between 410 and 660 kilometers deep. These inclusions provide our only direct samples of the deep mantle, offering glimpses into a realm that seismic waves can map, but that we could never otherwise touch. Another window into the mantle comes from mid-ocean ridges, where mantle material rises close to the surface and partially melts to create new oceanic crust. By studying the chemical composition of basaltic lavas erupted at these ridges, scientists can infer the composition of their mantle source. Different mid-ocean ridges produce lavas with slightly different chemistry, revealing that the mantle isn't perfectly uniform, but contains subtle variations in composition. Ocean island volcanoes, like those in Hawaii, provide yet another perspective on mantle composition. The lavas erupted at these hot spots appear to sample deeper parts of the mantle than mid-ocean ridges do, possibly including material from the lower mantle or core mantle boundary region. The trace element signatures and isotopic compositions of these lavas tell stories of ancient processes that separated different parts of the mantle billions of years ago. Laboratory experiments play a crucial role in mantle studies. Scientists recreate mantle conditions using high-pressure devices that can generate the extreme pressures and temperatures found deep within the Earth. Diamond anvil cells can create pressures equivalent to those in the lower mantle, while large multi-anvil presses can generate transition zone conditions on larger samples. These experiments allow scientists to determine how mantle minerals behave under deep Earth conditions and to calibrate the seismic observations. One of the most important experimental discoveries was the identification of the phase transitions that occur at 410 and 660 kilometers depth. By slowly increasing pressure on olivine samples, researchers found that the mineral transforms first to wadsleyite, then to ringwoodite, and finally breaks down into bridgmanite and ferropericlase. These laboratory results explained the seismic discontinuities observed at these depths and helped scientists understand the mantle's layered structure. Computational modeling has become increasingly important for mantle studies. Powerful computers can simulate the complex physics of mantle convection, allowing scientists to test their understanding of how the deep Earth works. These models combine information from seismology, geochemistry, mineral physics, and field observations to create comprehensive pictures of mantle behavior over geological time. The models reveal that mantle convection is far more complex than simple thermal circulation. Chemical variations, phase transitions, and the interaction with surface tectonics all influence the pattern of flow. Some models suggest that the mantle convects in two layers, with limited mixing between upper and lower mantle. Others support whole mantle circulation with material cycling from the surface to the core mantle boundary and back. Geochemical studies provide another powerful tool for investigating the mantle. By analyzing the isotopic compositions of volcanic rocks, scientists can trace the sources of mantle melts and understand how different parts of the mantle have evolved over time. Isotopes of elements like helium, lead, strontium, and neodymium act like fingerprints, revealing the age and history of different mantle domains. Some volcanic rocks contain isotopic signatures that appear to date back to Earth's earliest history, suggesting that parts of the mantle have remained isolated from surface processes for billions of years. Other rocks show evidence of recent interaction with recycled surface materials, indicating active mixing between surface and deep Earth reservoirs. Satellite observations contribute to mantle studies in surprising ways. Precise measurements of Earth's gravitational field can detect the subtle variations caused by density differences in the mantle. Regions where cold, dense material is sinking create slightly stronger gravity, while areas above, hot, buoyant upwellings, show weaker gravity. These variations, measured by satellites like GRACE, Gravity Recovery and Climate Experiment, help map the large-scale structure of mantle convection. Similarly, satellite measurements of tiny changes in Earth's rotation rate can reveal how mass is redistributing within the planet due to mantle flow. The shifting of material within the mantle changes Earth's moment of inertia, slightly affecting how fast the planet spins. These effects are incredibly small, but modern instruments can detect them and use them to study mantle dynamics. Recent technological advances continue to open new windows into the mantle. Improved seismometers can detect smaller earthquakes and more subtle signals from the deep Earth. New high-pressure experimental techniques can recreate conditions deeper in the mantle than ever before. Advanced analytical instruments can measure the chemical composition of smaller and smaller samples, revealing details that were impossible to obtain just a few decades ago. Perhaps most importantly, the integration of different approaches is providing increasingly complete pictures of the mantle. Seismic observations constrain the physical structure. Geochemical studies reveal the composition and evolution. Experimental work determines material properties, and numerical modeling ties everything together into coherent understanding of how the system works. The study of Earth's mantle represents one of science's great detective stories. Using earthquakes as messengers, volcanic rocks as samples, and laboratory experiments as tests, scientists have mapped and characterized a realm that remains forever beyond direct human experience. They have revealed the mantle to be not a simple uniform layer, but a complex, dynamic system with its own geography, its own weather patterns, and its own long history of evolution. Every new discovery about the mantle changes our understanding of how Earth works as a system. The techniques developed to study the deep Earth have also found applications in other fields, from monitoring nuclear weapons tests to exploring for oil and minerals. The quest to understand our planet's interior continues to drive technological innovation and scientific discovery. As we rest and contemplate these remarkable achievements, we can appreciate the ingenuity that allows us to explore the unreachable depths of our own planet. Through the careful analysis of earthquake waves, the patient study of volcanic rocks, and the creative application of physics and chemistry, we have learned to read the hidden stories written in the deep Earth. The mantle may be invisible to our eyes, but it is no longer invisible to our understanding. Our understanding of Earth's mantle continues to evolve as new technologies and discoveries reshape our view of this hidden realm. In recent decades, revolutionary advances in seismology, geochemistry, and experimental techniques have revealed aspects of the mantle that earlier scientists could never have imagined. Today's mantle is understood to be far more complex, dynamic, and influential than we ever realized. One of the most significant recent discoveries concerns the mantle's water content. For decades, scientists assumed that the deep Earth was essentially dry, with water being primarily a surface phenomenon. This assumption was overturned by the discovery that mantle minerals, particularly those in the transition zone, can incorporate significant amounts of water into their crystal structures. This isn't liquid water, but hydrogen and oxygen atoms bonded within the mineral framework. The implications of this discovery are profound. The transition zone between 410 and 660 kilometers depth may contain more water than all the surface oceans combined. This water affects the physical properties of mantle rock, making it more ductile and influencing how it conducts heat and electricity. The presence of water also affects melting behavior, potentially creating partially molten zones within the otherwise solid mantle. Evidence for this deep water comes from several sources. Laboratory experiments show that wadsleyite and ringwoodite, the high-pressure forms of olivine that dominate the transition zone, can contain up to 3% water by weight. Diamond inclusions containing these hydrous minerals provide direct proof that water exists in the deep earth. Seismic studies have identified regions in the transition zone where wave velocities are reduced, possibly indicating the presence of partial melts caused by water-induced melting. The water cycle of the deep earth operates on geological timescales. Water enters the mantle through subduction zones, where hydrated oceanic crust and sediments carry surface water into the deep earth. Some of this water is returned to the surface through volcanic activity, but some may be stored in the transition zone for millions or billions of years before being recycled back to the surface. Recent seismic imaging has also revealed new details about the large-scale structure of mantle convection. High-resolution tomographic studies have identified two massive structures in the lower mantle that appear to be fundamentally different from the surrounding material. These large low-shear velocity provinces, LLSVPs, sit above the core mantle boundary beneath Africa and the Pacific Ocean, each roughly the size of a continent and hundreds of kilometers thick. The African L appears to be connected to the surface expression of the East African Rift system and may be driving the breakup of the African continent. The Pacific LLS5P may be the source of the numerous hotspot volcanoes scattered across the Pacific Ocean, including Hawaii, Samoa, and the Marquesas Islands. These structures appear to have been stable features of the deep mantle for hundreds of millions of years, suggesting that they play a fundamental role in organizing global mantle flow. The composition of these LLSVPs remains controversial. They may be chemically distinct from the rest of the lower mantle, perhaps representing ancient material from Earth's early differentiation, or accumulations of recycled oceanic crust. Alternatively, they might be purely thermal features, regions where the mantle is significantly hotter than average. Their low seismic velocities could result from either compositional differences or higher temperatures, and distinguishing between these possibilities remains one of the major challenges in mantle research. Another area of active research concerns the behavior of subducted oceanic plates within the mantle. Advanced seismic imaging can now track these cold slabs of surface rock as they descend through the mantle, revealing their fate in unprecedented detail. Some slabs appear to stagnate in the transition zone, piling up at the 660-kilometer discontinuity like traffic at a bottleneck. Others penetrate into the lower mantle and can be traced all the way to the core mantle boundary. The interaction between descending slabs and the large-scale mantle flow pattern creates complex three-dimensional structures. Cold slabs can deflect and organize mantle plumes, while hot upwellings can affect the trajectories of sinking slabs. This interaction helps explain the observed correlation between surface volcanism and the locations of ancient subduction zones, even when those subduction zones are now thousands of kilometers away. Recent discoveries about the core mantle boundary have also changed our understanding of deep Earth processes. This boundary, located 2,890 kilometers below the surface, is not the simple interface between liquid iron and solid rock that scientists once imagined. Instead, it appears to be a complex zone with its own unique properties and processes. The D layer, a thin region just above the core mantle boundary, shows evidence of extreme compositional and thermal variations. Some regions may contain iron-rich material that has leaked from the core into the mantle. Other areas show evidence of chemical reactions between mantle rock and the liquid iron core, creating new phases that exist nowhere else on Earth. Post-perovskite, a newly discovered high-pressure phase of bridgemanite, appears to be stable only in the extreme conditions of the D layer. This phase transition may explain some of the complex seismic signatures observed in this region and could influence the pattern of heat flow from the core to the mantle. The dynamics of the core-mantle boundary also affect Earth's magnetic field. The liquid iron core generates our planet's magnetic field through a complex dynamo process. But this process is influenced by the pattern of heat flow across the core-mantle boundary. Variations in the thermal conductivity of the D layer may create patterns of heat flow that organize the motion of liquid iron in the outer core, ultimately affecting the strength and stability of the magnetic field. Modern research has also revealed new aspects of mantle plume behavior. Rather than being simple, steady columns of hot rock, plumes appear to be complex, time-variable features with their own internal structure. The heads of large plumes may be compositionally different from their tails, carrying different chemical signatures from their deep source regions. Some plumes appear to be episodic, pulsing on time scales of millions of years rather than flowing steadily. The relationship between mantle plumes and surface volcanism is also more complex than originally thought. Not all hotspot volcanoes appear to be fed by deep mantle plumes. Some may be shallow features related to local mantle circulation, or the interaction between regional tectonics and mantle flow. Distinguishing between deep plumes and shallow upwellings requires careful analysis of the chemical signatures of volcanic rocks and the seismic structure beneath hotspot volcanoes. Advances in experimental mineral physics have revealed new details about the properties of mantle materials under extreme conditions. Studies of bridgemanite, the most abundant mineral in the lower mantle, have shown that it can exist in different forms depending on the exact pressure, temperature, and chemical conditions. Ion spin transitions in bridgemanite and ferropericlase may affect their thermal and electrical properties, potentially influencing heat transport in the lower mantle. The discovery of new high-pressure phases continues to surprise scientists. Recent experiments have identified previously unknown forms of silicate minerals that may be stable under lower mantle conditions. These discoveries suggest that the mineral physics of the deep Earth is even more complex than previously thought, with implications for our understanding of mantle convection and evolution. Isotopic studies of volcanic rocks continue to reveal new aspects of mantle evolution and dynamics. High-precision analysis of isotope ratios in mantle-derived rocks provides information about when different parts of the mantle were isolated from each other and how they have evolved over geological time. Some isotopic signatures appear to require storage in isolated mantle reservoirs for billions of years, suggesting that mantle mixing is incomplete on even the longest timescales. The integration of seismic, geochemical, and experimental data through numerical modeling has led to increasingly sophisticated understanding of mantle convection. Modern computer simulations can incorporate realistic mineral physics, complex chemistry, and the interaction with plate tectonics to create comprehensive models of mantle behavior. These models suggest that mantle convection operates as an integrated system, with processes in different layers and regions influencing each other over geological time. Climate connections to mantle processes have also become increasingly apparent. Large igneous provinces, massive volcanic eruptions that cover millions of square kilometers, appear to be linked to the arrival of large mantle plumes at the surface. These eruptions can affect global climate by releasing enormous amounts of volcanic gases into the atmosphere. The Deccan Traps eruption, 66 million years ago, linked to the Réunion hotspot, may have contributed to the mass extinction that ended the Cretaceous period. The long-term carbon cycle also involves mantle processes. Carbon dioxide released by volcanic activity returns carbon from the deep Earth to the atmosphere, while subduction zones carry surface carbon back into the mantle. The balance between these processes helps regulate Earth's climate over geological timescales, suggesting that Mantle convection plays a crucial role in maintaining the conditions necessary for life. Future research promises even more discoveries about the mantle. New seismic arrays are providing higher resolution images of mantle structure. Advanced experimental techniques are pushing the boundaries of achievable pressure and temperature, allowing laboratory studies of lower mantle conditions. Isotopic analysis is becoming more precise, revealing ever more subtle details about mantle evolution. The emerging picture of Earth's mantle is one of extraordinary complexity and interconnectedness. Far from being a simple, uniform layer, the mantle is revealed as a dynamic system with its own geography, chemistry, and evolution. Its processes connect the deepest parts of our planet with the surface environment, influencing everything from the position of continents to the composition of the atmosphere. Understanding the modern mantle requires integrating observations and theories from many different fields: seismology, geochemistry, mineral physics, fluid dynamics, and even climate science. This interdisciplinary approach continues to reveal new connections and processes that earlier, more specialized studies missed. As we contemplate these recent discoveries, we can appreciate how much our understanding of Earth's interior has advanced in just a few decades. The mantle that scientists study today is far more complex and fascinating than the relatively simple layer imagined by earlier generations of researchers. Yet each new discovery raises new questions, ensuring that the study of Earth's mantle will continue to be an active and exciting field of research for many years to come. As our journey through Earth's hidden engine draws to a close, let us settle back and reflect on the magnificent realm we've explored together. The mantle, stretching from just beneath our feet to nearly halfway to the center of our planet, represents one of nature's most extraordinary achievements, a system so vast, so complex, and so enduring that it has shaped every aspect of our world for over 4 billion years. Think about the incredible story we've witnessed. We began with a young, molten Earth, born from cosmic violence and slowly cooling into the layered structure we know today. We explored the mantle's architecture, its distinct layers, each with their own minerals, their own properties, their own role in the grand design. We discovered its composition, from the familiar green olivine of the upper mantle to the exotic bridgemanite that makes up more of our planet than any other single mineral. We witnessed the endless dance of convection, where solid rock flows like honey over geological time, carrying heat from the deep earth to the surface in currents that have never stopped moving since our planet's youth. We saw how these deep currents reach upward to drive plate tectonics, moving continents across the globe, building mountains, opening oceans, and constantly reshaping the surface of our world. We marveled at the ingenuity of scientists who have found ways to study this unreachable realm, using earthquake waves as messengers, volcanic rocks as samples, and laboratory experiments to recreate the extreme conditions of the deep Earth. And we explored the cutting-edge discoveries that continue to reveal new aspects of this hidden world, from the vast reservoirs of water in the transition zone to the mysterious structures at the core mantle boundary. Throughout this journey, one theme has remained constant. The mantle is not separate from our surface world, but intimately connected to it. Every breath we take includes gases that have cycled through the mantle. The ground we walk on was shaped by mantle processes. The metals in our technology, the nutrients in our soil, even the water in our oceans, all have been touched by the great engine beneath our feet. The mantle teaches us about the power of patient, persistent processes. Nothing in the mantle happens quickly by human standards. Convection currents move at the speed of growing fingernails. Mantle rock takes millions of years to complete a single circuit, from deep earth to surface and back again. Yet these slow processes have accomplished extraordinary things. They have built continents, created ocean basins, and maintained the conditions necessary for life to thrive. there is something deeply peaceful about contemplating the mantle's slow rhythms. While our daily lives move at ever-increasing speeds, the deep Earth operates on time scales that dwarf human experience. The currents flowing beneath us now began their journey before humans existed. The heat they carry originated in the formation of our solar system. The minerals they transport have been cycling through Earth's interior since before life appeared on our planet's surface. This perspective offers a kind of geological meditation. Our concerns and worries, important as they are to us, are momentary fluctuations compared to the steady, patient work of the mantle. The anxiety that keeps us awake at night is insignificant compared to the deep stability of Earth's interior processes. The mantle reminds us that our planet operates on scales of space and time that can put our daily troubles into perspective. Yet the mantle is not just ancient history. It continues to shape our world today, and will continue to do so for billions of years into the future. The mantle plume beneath Yellowstone will eventually produce another massive eruption. The East African Rift will continue to split the African continent. New ocean basins will open, and old ones will close. Continents will drift to new positions, changing climates and ecosystems in ways we can barely imagine. The mantle also connects us to the broader cosmos. The radioactive elements that heat our planet's interior were forged in the nuclear furnaces of ancient stars. The iron that makes up Earth's core was scattered through space by stellar explosions billions of years ago. The mantle represents our planet's participation in the cosmic cycles that connect all matter in the universe. Understanding the mantle helps us appreciate Earth's uniqueness among the planets we know. Mars, smaller than Earth, lost its internal heat long ago and now has a largely inactive interior. Venus may still have mantle convection, but its thick atmosphere prevents us from seeing the surface effects. Only Earth has maintained the delicate balance of size, composition, and thermal evolution that allows for active mantle convection coupled with a diverse surface environment. This active mantle has been essential for life's evolution and survival. Without mantle convection to drive plate tectonics, Earth would lack the continental platforms where complex life evolved. Without volcanic outgassing from the mantle, our planet would have no atmosphere or oceans. Without the deep carbon cycle that connects surface and interior, our climate would be unstable and probably uninhabitable. The mantle has also provided the raw materials for our civilization. The metals we mine, the building stones we quarry, even the fossil fuels we burn, all ultimately derive from mantle processes. The magnetic field that protects us from harmful solar radiation is generated by core convection that is driven by heat from the mantle. In countless direct and indirect ways, the hidden engine beneath our feet makes our modern world possible. As we prepare for sleep, we can take comfort in the mantle's steadfast presence. While we rest, the great currents will continue their slow circulation, carrying heat from the deep Earth toward the surface. New oceanic crust will form at mid-ocean ridges. Old crust will descend into the depths at subduction zones. Mantle plumes will continue their long journey toward the surface, eventually creating new volcanic islands or continental flood basalts. This continuity is reassuring. Long after our individual lives are over, long after our civilizations have risen and fallen, the mantle will continue its patient work. It will continue to shape the surface of our planet, continue to regulate its temperature, continue to provide the dynamic foundation that makes Earth a living world rather than a dead, static ball of rock. The mantle embodies the principle that small forces, applied consistently over vast periods of time, can accomplish extraordinary things. Just as water can carve the Grand Canyon given enough time, The gentle flow of mantle convection has built continents and ocean basins, created mountain ranges and ocean trenches, and established the framework within which all of Earth's surface processes operate. Perhaps there is a lesson here for our own lives. The most important changes often happen gradually, almost imperceptibly, through the accumulation of small, consistent efforts over time. Like mantle convection, the most powerful processes in life are often the slow, patient ones that work steadily toward their goals without fanfare or immediate recognition. As sleep begins to carry you away, let your mind drift with the slow currents of the mantle. Feel yourself connected to the deep rhythms of our planet, to the ancient processes that have been shaping our world since long before consciousness evolved to contemplate them. Rest in the knowledge that you are part of something vast and enduring, something that connects you to the deepest foundations of existence. The mantle will continue its work while you sleep, just as it has every night for billions of years. In its patient, persistent circulation, we find a model for endurance and a source of comfort. The hidden engine of our planet beats with a rhythm slower than any heartbeat, breathes with cycles longer than any lifetime, yet it is as constant and reliable as anything in our universe. Sleep well, fellow travelers. Dream of deep currents and ancient heat, of patient time and enduring stone. Dream of the hidden engine that has made our world possible, and that will continue its faithful work long after we have become part of the eternal circulation ourselves. In the mantle's endless dance, we glimpse something of the deep stability that underlies all change, the quiet persistence that makes all transformation possible. Good night, and may your rest be as deep and peaceful as the currents flowing in Earth's hidden heart.